Now I know you already filled these in, but let's just look at a minus 80 to 5. Now this was really just the middle. And then this gave us that distance. So I could also think of it like the difference gives us the distance. So how far will it go to the left and how far will it go to the right is sort of locked into here. And the reason I point that out is because as we're looking at this distance between these two different objects, well, we're wavering between a midpoint. Then those are arrows to the left and right. And so what I'm saying by this is that if I just count how far away these are from each other, or I can even think, well, 1 over, back 1, 1 more over, back 1, 1 over, back 1, that puts me at 6. The other thing I could do is I could just count the distance in between these, and I could say, well, they are really 6 apart from each other, and so that means that if I went halfway from 3 up, that would put me to 6. And then same way as starting at 9, if I backed up 3, I would get to that 6. And you could also do 9 minus 3 and then divide that by 2. But what I'm pointing out is that the distance from the center is really just 3 units. And so when I want to find the distance, either of these is from 6, there I go. So these are always going to be set up to where you kind of have the distance from the midpoint. So there's my midpoint, like it's at 6. And then this would be like, half the distance if you wanted that with d over 2. Whatever makes most sense to you. They don't get too deep into the actual reasoning behind this. They kind of just show you how to do this in this textbook. So I think it helps to see the meaning. Well, let's, do some extra work. And I will show this in regular font and not just red, but I'm going to put check. And we'll check it because if we check it, it's going to help us believe it a little bit more. So we'll check it as a positive case, and we'll check it as a negative case. So let's solve this. X minus 6 equals 3. Add 6 to both sides, and that gives the x is 9 upper boundary of this absolute value. And then in the negative case, x minus 6 giving me negative 3, I can add 6 to both sides, and x ends up being 3, which I get in the lower case. So the cool thing is, by doing this check, it helps me see that the answer we thought might work ends up being the correct answer. But for problem 2, we won't bother with that. We'll just jump in. So we normally have it set up to where there's x minus some number is going to be equal to another number. So if I look at these, you kind of just have to jump back in between your notes, and maybe this is a little bit of a weird one, but you kind of have to double check this type of problem as you head into a test to make sure you got the difference between what goes here and what goes here, even when it's sort of subtle and hard to figure out. So however you're going to do this, but I like to just look at the middle, and this one's close enough to where you can just see it. And so I'm going to say, well, the middle is at 3. And if I wanted to, I could see, well, the total distance is 4, and if I just go half of 4, that's 2. So does the half number go on the inside of the absolute value or on the outside? We look at the previous one, you kind of reason through it, figure out what makes sense. Well, the distance is going to be 2. The distance is what you get when you calculate an absolute value. And what we're doing is we're finding out how far from center that is, so we're doing x minus 3 to get to that 2. So for this, maybe we just think, well, 5 is an answer, and if I plug 5 in, 5 minus 3 gives me 2, so I know I'm good there. If I plug 1 in, well, 1 minus 3 gives me negative 2, and the absolute value of that is 2. That's all you have to do for these problems. So if it seems like I'm making it difficult and it seems more easy than I said, to you, well, that's a great thing. That means you understand it. Okay, now we're told to graph each function and then state the domain and range of each function. Now you'll notice that I didn't give you any graphing paper for this, and I did that on purpose. So let's set up x as a table for these new ones, and then y. Now for this first part, we know that there's a point at which this absolute value of x switches from being a negative situation and a positive situation. Well, if I plug in a positive 3, I just get 3. If I plug in a positive 2, I get 2. If I plug in a positive 1, I get 1. 0, I get 0. But then when I go back and I plug in a negative 1, I get positive 1. So it's very clear to me that when this goes from 0 to being negative, like even if it's negative 0.1, or from 0 to 0.1, its behavior changes. And when we think about 0 as being the mid-center, maybe I count 1, 2, 3, 4, 5 total spots, and then I'm thinking, well, I want to see how this behaves around 0 for x, so I'm going to walk back negative 1, back another negative 1 to negative 2, and then forward. So, we can show our work for this, or we can just be like, the absolute value of negative 2 is 2. And then I'll fill that in. The absolute value of negative 1 is 1. And so similarly, I'll fill that in. The absolute value of 0 is 0, the absolute value of 1 is 1, and 2 is 2. Now, when I want to budget my space for this, I'm setting up my table on the left, and then on the right side, I'm making a nice symmetrical graph using my ruler, and I'm thinking I'm going back negative 5, symmetrically forward 5, 1, 2, 3, 4 tick marks, 1, 2, 3, 4 tick marks. And then this only goes into the positives, but I think it's fine to just have a setup like I've done. There's 5 and 5, also symmetrical. 1, 2, 3, 4, 1, 2, 3, 4. And so when I'm back negative 2, I'm up 2, and I can think of those as coordinates. Back 1, up 1, and then 0, 0, and then forward 1, up 1, 2, 2. And so what I now have is not just a straight linear relationship. I actually have a couple straight lines, and this forms a V shape, and that should be new to you. So what you're looking at is the function of an absolute value. This is what absolute values look like. And this always made sense to me that they should look like this because, it's a normal linear relationship, but then at some point it's going to ricochet. Maybe it does it down here. Maybe it's even upside down and does it in that direction. You can also have ones that are super narrow or super wide. These behave in all sorts of different ways. And we can check out some of this in GeoGebra if you would like. But until we really feel comfortable with it, we're figuring out, well, let's build a table, then graph the points, and then graph that line. And since we're becoming better and better graphers, let's label the equation. It's just y equals, but we write f of x because it's a function, is the absolute value of x. And then that's clearly labeled, and everybody can trace our work. We have one more requirement for this problem. I'm going to erase what I have here because I want it to be clear that I'd usually write this in the same lines if I could. So for the domain, you'll remember that domain talks about all the different x values. Well, it looks like x could be 0. It looks like it can be 1, 2, 3, 4. It looks like as long as we keep heading, in the right direction, we'll get a value for x. And the same deal for the left direction. So we'll always be able to have any answer we want for any x we plug in. So I'm going to say x is a double struck r, which means all the real numbers. So x is all the real numbers. You can also see this later on written as negative infinity to infinity. But when I look at this graph, it's clear that when I'm dealing with the range, or my y values, I can come back to the graph, and I will have a y value there, and I will have a y value there. And if I kept on going higher and higher, it looks to me like as long as I plug in some x, I will get some positive y. So all these y's are solutions up here. But when I come down closer to the x-axis, I don't get any y values down here. And so if this were like in the Star Wars movies, where they have the trash compactor scene, and I were try to flatten everything into the y-axis, all my points would get flattened here, but there's no points getting flattened in here. And I can make that more clear by talking through this with you if you want to see it. So for y, I will say y is greater than or equal to 0. We get a positive value whenever we plug these in, but we're never going to get negative values out of this particular function. So this is the parent function, where it's just the absolute value of x. Anything more complicated than that, and it's going to be a little bit more involved. And so speaking of being a little bit more complicated, this next one is. So here's f of x is equal to x minus 4. Now I'm encouraging you to think about these more deeply than the textbook and other teachers might. So here's x and here's f of x. And the reason I'm encouraging you to think of it more deeply is because it'll be a time saver in the future, and it'll also help these functions make sense so you can learn way and way more complicated ones. Well, imagine that instead of x minus 4 in here, you just have a big blob of nothing. Well, whenever you take the absolute value of something, it starts to act strange when it gets to 0. But since we don't have just 0 in here, we have x minus 4. Over on the side of my paper, maybe off to the side, I'm thinking, well, when will x minus 4 be 0? Because that's what's going to, the whole function will switch from being negative to positive, which means that that's when my v will occur, that v shape that we saw in the last one. Well, easy enough. That means that x is going to be 4. And the reason I point this out is because if I choose 4 down here, and it's easier to count up to 5, 6, because then I establish my pattern of counting backwards, 3, 2, we're going to see that the points I've chosen really get me to see how my V shape behaves and where it will be, rather than just like randomly choosing different points to plug in. So in my head I'm doing this, but you can always write this out. Starting with the top, 2 minus 4 gives me negative 2, and the absolute value of negative 2 is positive 2. 3 minus 4 is negative 1, and the absolute value of negative 1 is positive 1. 4 minus 4 is 0, and the absolute value of 0 doesn't matter at all, it's just 0. And then 5 minus 4 is, it looks like times, but 5 minus 4 is 1, and the absolute value is 1. And then 6 minus 4 is 2. And the cool thing is, for all you guys noticing the pattern, it bounces right there, so that gives me the V shape. And by choosing those points, it makes graphing it a much clearer concept. Same deal as before, setting these up to be symmetrical as best you can. I've moved it over and set up boundaries of 5. Hopefully you're filling this in with similar accuracy to mine. And then when I go and I plot these points, I have 2, 2. Let me make that stand out in a different color. 2, 2. 3, 1. 4, 0. 5, 1. 6, 2. And then let's see if I can get this V shape. Now I'm going beyond what I've written. That's because I kind of need to make quick movements. Now this might look like it's flatter than the other one, but that's just the way that I've graphed it. This would actually have the same slope as the last one did. So this is a pretty good looking graph. And then when we think about the domain, and we think about the range, well, it looks like I can go on forever to the left and forever to the right. So just like the last one, x is going to be the element of all the real numbers. So there's my double struck R. It's kind of like a wide R with a fatter top and then a T connecting it. Okay, so with the range though, same as before, I'm going to flatten everything towards the y-axis. And when I think of everything moving in towards the y-axis and getting smushed from both sides, I'm seeing that there seems to be a cutoff right there. So just like the last one, y would have to be greater than or equal to 0. So we're stating the domain and range. Now as you see these patterns, you probably are like, well, I guess it's always going to be that way. Don't let that mislead you for these problems. Usually you can plug in anything for x, but for y, it's not necessarily always at 0. Okay, this is more complicated. The reason it's more complicated is because it involves a little bit of a fraction problem in a moment. So like if this were your homework, you'd write f of x equals the absolute value of 2x plus 1. And when I go to set up my graph, I have x, f of x. Most people would say table. You call it a graph too. Be flexible. But I'm thinking, well, okay, 2x plus 1. When does that equal 0? Because that's what's on the inside. And then maybe you're like, well, it's when x is negative 1/2. So a little frustrating to have to deal with fractions in this one. So here's negative 1/2, but then I'm going to walk forward an entire step, which puts me at 1/2, and then forward another step puts me at 3/2, and then when I go in the opposite direction, here's negative 3/2, negative 5/2. And this is where you probably pull a calculator out and start typing these in. Or you can be like, well, 2 times negative 5/2 is negative 5, plus 1 is negative 4. 2 times negative 3/2 is negative 3, plus 1 is negative 2. Well, 2 times negative 1/2, that's negative 1 plus 1 is 0. And where you're going to feel more confident dealing with these fractions is making the guess. Well, it should be 2, shouldn't it? It should kind of bounce right here. And if it isn't, that means we may have made a mistake. So 2 times 1/2 is 1, plus 1 is 2. And that's where you get that kind of warm, fuzzy feeling of knowing that chances are you made the right call here. 3/2 times 2 gives me 3, plus 1 is 4. And when we graph this, looks like we might want to go just negative 5 to 5. And your graph will probably be more challenging than the last one because of all the decimals. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then we have negative 5/2, negative 4. So that means you're at like negative 2.5 and then down 4. The negative 3/2 is the same as negative 1.5 and down 2. And then 0, at negative 1/2 we have 0. And then at 1/2 we have 2. And you might have realized something that I didn't realize because I'm probably thinking about too many things. Well, this isn't a V. And if it's not a V, that means we made a mistake. And when I look at this, I'm like, well, you know what I forgot to talk about when I was plugging these numbers in? I forgot to take the absolute value of everything. And now if I go back and I take the absolute value of everything, I need you to sneak in and erase those negatives in front of those 4s and 2s, so that then I can switch the location of these points so that they're above the y-axis and get a different V-shape than we had in the last one. And this will definitely be more of a narrow and faster ascending V-shape than we had before. I apologize for that. We can go over that if it threw you off. But it really wasn't most of the problem. It was just that small part. Now let's talk about the domain. Well, the domain, it looks like it's just the same as before. X is all the real numbers. And then the range is the same as the last one, but like I told you, it's greater than or equal to 0, but it's not always going to be that way. And you will be like, well, why'd you make us do all that with the fractions and everything? Guess what? You might feel comfortable with the easier way, and then we're going to want to do the easier way. But it's actually the wrong decision because the textbook isn't preparing you for what's to come in like your more Algebra 2 and college algebra classes that you'll eventually have to take, where the teacher will just assume that you guys know that stuff. So don't dodge the more challenging problems for now, and hit me up with help on those last graphing ones, because they're pretty cool, but they're also aided by using softwares like GeoGebra, because you can actually see it manipulate and change.